In chapter 6.7, we're going to introduce the hyperbolic trig functions. So, in actuality, the hyperbolic trig functions are not trig functions, they're exponential functions. Or in this case, you notice they're a combination of e to the x minus e to the negative x in some way. So like for instance, hyperbolic sine is e to the x minus e to the negative x divided by 2. Hyperbolic cosine is e to the x plus e to the negative x divided by 2. And then all the other hyperbolic trig functions will be defined as some quotient of those. So hyperbolic tan is hyperbolic sine over hyperbolic cosine. Hyperbolic cosecant is 1 over hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. And hyperbolic cotangent is hyperbolic cosine over hyperbolic sine. So the reason that we're relating these to the trig functions is because what we'll notice is that they have a lot of properties that are very similar to those trig functions, but we have to be careful. They're a little bit different, and in particular, we know that they're not periodic like trig functions are. So, for instance, a hyperbolic sine doesn't repeat itself periodically, or same with hyperbolic cosine. But they do maintain a lot of the properties that those other trig functions, the traditional trig functions, really do have. So we'll kind of try and recognize how they're similar. So let's just look at their graphs really quick. We notice that, for instance, hyperbolic sine is a combination of 1/2 e to the x minus 1/2 e to the negative x. So if I combine those two exponential curves together, we get the curve of hyperbolic sine, which we notice is this red curve here. Notice it has some symmetry. It's an odd function because it's symmetric about the y-axis. Or I'm sorry, it's symmetric about the origin. If I rotate this 180 degrees, we get that odd symmetry. Passes through 0, 0. Hyperbolic cosine is a little different. It's a combination of 1/2 e to the x plus 1/2 e to the negative x. So we see those two curves here. If I combine those two curves together, we get the red curve. And this red curve is an even function, right? It has that even symmetry. It's symmetric about the y-axis. It passes through the point 0, 1. Yeah, and it's not quite a parabola, but it's a U-shaped graph. And let's look at also what hyperbolic tangent looks like. Remember, hyperbolic tangent we've defined as the hyperbolic sine over hyperbolic cosine. So in a way, it's the same thing as 1/2 e to the x minus e to the negative x on the top, and then 1/2 e to the x plus e to the negative x on the bottom. Okay, and what you notice here is those factors of 1/2 will cancel. As x goes to infinity, what happens is x goes to infinity. Well, one thing I noticed is that as x goes to infinity, we could rewrite, if I divide out e to the x, for instance, this would be something that looks like this. If I divide the top and bottom by e to the x. So as x goes to infinity, these terms e to the negative 2x both go to 0. So I'm left with 1. So as it goes to the right, it approaches 1. Or similarly, if I divide out e to the negative x instead, then we would have e to the 2x minus 1 over e to the 2x plus 1. So we see now as x goes to negative infinity, e to the 2x will go to 0. So this goes to negative 1 over 1. So it goes to negative 1 as it goes to the left. So you can kind of see just by manipulating it algebraically like that, we get those horizontal asymptotes. Notice this kind of looks similar to the graph of tangent inverse. But it certainly doesn't look like the graph of tangent. Same with the hyperbolic sine and hyperbolic cosine. They look nothing like the graphs of sine and cosine. Why are these useful ones to consider? Well, they have a lot of applications, especially in physics and engineering. Here's just two really really simple examples that we might explore later on. One is a catenary. A catenary is a weighted cable that's hanging between 2 points, and the way that cable is or the shape that cable forms as it's suspended from those 2 points is called a catenary. Another application is it can be used in the formula for an idealized ocean wave, and this comes from solving a certain differential equation. And in this case, what we see is that it's related to both the depth of the d would be the depth of the water, L would be the length of our wavelength, right? And g would be the gravitational constant. So as a function of those different variables, we can model the velocity of an ocean wave. Here's some interesting identities that we actually notice just right off the bat look very similar to the trig identities. For instance, we notice that here sine is an odd function, so our hyperbolic sine is an odd function. It's an odd function. We notice that in the graph it had that odd symmetry. Hyperbolic cosine is an even function, right? So it satisfies the property that hyperbolic cosine of negative x equals hyperbolic cosine of x, so it's an even function. We have something a little bit different than the Pythagorean theorem for sine and cosine. We know that if I do sine squared plus cosine squared, we get 1, but here it's going to be hyperbolic cosine squared minus hyperbolic sine squared. That'll equal to 1. For tangent, we get something similar where it's 1 minus hyperbolic tan squared equals hyperbolic secant squared. But in this case, it's relating hyperbolic sine and hyperbolic cosine, or in this case, it's relating hyperbolic secant and hyperbolic tangent. And then we also have these sum and difference formulas. But let's try and prove one of these so we can kind of see why these formulas are the way they are. Suppose I want to prove the identity hyperbolic cosine minus hyperbolic sine squared is equal to 1. Well, let's write out what these exactly are. So hyperbolic cosine, we know, is 1/2 e to the x plus e to the negative x, and then we're squaring it. Hyperbolic sine was 1/2 e to the x minus e to the negative x, and then we're squaring it. Let's square these out. So 1/2 squared would be 1/4. E to the x plus e to the negative x. When I square that out, we're going to do a little foiling. Will be e to the 2x plus 2e to the x. E to the negative x is just 1, so just 2 there. Plus e to the negative 2x. Okay, so just foiling that out gives me what we have there. And then minus here again 1/4 when we square 1/2, and then foiling out e to the x minus e to the negative x, we'll have e to the 2x minus 2, right? Because 2 times e to the x times e to the negative x will be just 1. and then plus e to the negative 2x. Alright, and then let's see what we can do from here. Well, first of all, I notice that a bunch of terms are going to cancel. So in particular here, e to the 2x minus e to the 2x, those terms will cancel. E to the negative 2x minus e to the negative 2x, those terms will cancel. So actually all that remains is 1/4 times 2 minus 1/4 times negative 2. So negative 1/4 times negative 2 will become positive 1/2. So we get 1/2 plus 1/2 is 1. And let's see if we can do something similar here. 1 minus hyperbolic tan squared. We could write this out as so we could write this out in terms of the exponential functions and work it out that way, but I'm thinking it might be easier if we start with this identity that we already proved, because we've already proved that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. And we know that those are all going to be related to the hyperbolic tangent and hyperbolic secant. In fact, we know how to get them. If I divide each of these two sides by hyperbolic cosine, then on the left side we have cosine squared minus divided by cosine squared will be 1. Hyperbolic sine squared divided by hyperbolic cosine squared, well, that's going to be hyperbolic tangent. And then 1 over hyperbolic cosine, we know that's hyperbolic secant. Okay. So since we've already established this first one, we can then use that to establish this next one.